Now we're going to come back to transformations of functions. And this will be very introductory, and later in the year we're going to go into much more detail about transformations of functions. And we touched on this a little bit with linear equations, but now we can apply the same concepts to other types of functions. So we have 4 of our common parent functions that we are going to be using. We've been dealing with linear and quadratic. And so in function notation, we have f of x equals x, or the equation y equals x. And we can see that we can plot these ordered pairs. We can find some x values, we get our outputs, and we have this straight line. Quadratic equations in function notation or with y equals x squared. And again, some xy charts to evaluate, and we can plot the graph. We see some of these points here. Absolute value gives us our V shape, and our square root graph has this arch, which is half of a parabola turned sideways. So these are our parent functions. Every single linear, quadratic, absolute value, or square root equation is based off of these shapes. And the way we get our other equations graphs is by transforming them. We can move them, we can flip them, we can stretch them, we can compress them, we can get them all over the place. And we're going to look at how some of these transformations work. So first, let's start by comparing these two linear equations, f of x and g of x. Well, we look at the slope of f of x, and we see that the slope is 1. Up 1, right 1, a rise of 1, and a run of 1. And g of x has the same slope, a rise of 1 and a run of 1. When we look at the equation, we see the slopes are 1. The y-intercept for f of x, since b is 0, our y-intercept is 0, 0, and we see that graphically here. But for g of x, since b is 3, our y-intercept is 0, 3, and we see that graphically here. And so what we can do is we can say that g of x is actually the function f of x, but it's shifted. It's moved k units up. And in this case, it's moved 3 units up. We call that our k value when we're dealing with a transformation. And if we had minus a number, we could say that we shifted k units down. And so we took this graph, and we took every single point on it, and we moved it 3 units up. We can do the same thing with nonlinear functions. If we look at f of x is x squared and g of x, we can see that for g of x, every single point on the graph is shifted the same number of units up, 2. So g of x is f of x shifted or moved 2 units up. This idea allows us to sketch parent functions and their transformations much more quickly without having to identify new ordered pairs. And we're going to talk about other transformations as well. So if we remember that a quadratic graph follows the same 5 ordered pairs, 0, 0, 1, 1, 2, 4, and these reflected points on the other side, we know that f of x, x squared, is always going to be this shape. And if I want to just quickly graph g of x without plotting any points, all I have to do is take this function and move it down 4 units, because we're shifting down 4. And so we know that it's going to go 1, 2, 3, 4, and everything is just going to move down 4 units from where it was before, and now I have g of x without having to do any additional calculations. If we're looking at the square root of x, we know the square root of x is going to make this shape. If we wanted to be a little bit more precise, we know it's going to make this shape here. And then in order to graph g of x, we look at our shift, and this is going up 2 units. And so everything is going to shift up 2 units. And I was able to graph it really quickly without having to do any additional calculations. Absolute value graphs, these are the easiest in my opinion, because they make that V shape on the origin. We don't really have to graph any points. We just know that it starts at the origin. And then we look at our transformation and say, okay, well this goes down 1 unit. So I just take both of those lines and I shift them down 1 unit. And now I have my transformation for g of x. Let's look at another type of transformation by comparing these functions using a table of values. So notice now how that addition or subtraction is inside of our grouping symbol. And let's take a look at how that kind of affects our graph. So it's not going to move it up and down. If I had the square root of x minus 2 with the minus 2 on the outside, we know that would move down 2 units. But let's see how this works differently given that the minus 2 is on the inside. So we have x equals negative 3. If we evaluate negative 3 minus 2, we get negative 5, and the absolute value of which is 5. So I have the point negative 3, 5. Now on the onset, it looks like maybe my point moved up 5 units, but that doesn't make sense because it would have to be the absolute value of x plus 2 in order for it to move up 2 units. And it's not, it's x minus 2 inside the absolute value. Okay, well let's keep following this pattern and see what happens. It's not until this point where we start to see y values repeat, which shows where the bounce is in our absolute value. And so if we plot these points, it looks like all of these are moving up until we get to here. Well, then I have the point 1, 1. Well, the point 1, 1 isn't shifted up 2 spaces, it's on the line. And then we have the point 2, 0. That's not shifted up. That's now below where it was, and then it bounces back up. So if we see the V pattern, it's a little bit easier to see what the transformation was. Our graph didn't shift up, it shifted to the right. All of those points moved right 2 units from the parent. So when we have something inside of our grouping symbol and we're taking x and we're subtracting an h value, that's going to shift our graph h to the right. Notice how it's kind of backwards here. We're subtracting something, but we're moving to the right. If we're adding something, we're going h units left. So our horizontal shifts are backwards compared to our vertical shifts. Let's take a look how that'll help us graph some things. So starting with our parent function x squared, something pretty basic, we have our parabola here. And so I can just quickly sketch the parent function. And you want to get to the point where the parent functions are pretty quick and easy to sketch. When you're looking at graphs, you should be able to determine what the shifts are pretty easily. And so our parent function is going to be right about here. Now we want to look at what our shifts are going to be. Well, inside here we have x minus h, which means we're going to go to the right 2 units. And out here we have plus k, which means we're going to go up 1 unit. So we take all of these points and we go right 2, up 1. 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 This one. And we see our parabola taking shape. And so here we have our g of x shifted to the right 2 and up 1 unit. Ignore the fact that this line is very wobbly. Now, the benefit of understanding transformations really comes into making our lives easier when we're looking at and trying to graph our functions. Because before, when we were trying to graph our functions, we had to find enough x and y values until our pattern took shape. And we were always kind of looking for where that starting point was. Well, by using these transformations, we know where the starting point is going to be. If our starting point on f of x is at 0, 0, and we know that g of x is going to be right 3 units and up 1 unit, we now know where our new starting point is. And so then we can graph much more reliably because we know that we're going to start at 2, 1, and then our quadratic is going to look like this. And so we just need to get a couple points to see exactly how that graph shows up. Similarly, if we have a square root equation, we know that our square root equation is going to start out like this. And so if we can identify the shifts that are going to happen, we can predict where our new function is going to be. Since we have x plus h, that means we're going to go left 4 units. And we have plus 3, which means we're going to go up 3 units. So g of x will be located left 3 units, or 4 units, and up 3 units. I know my new graph is going to be somewhere over there on the left. So if I know my parent function looks something like this, if I go left 4 units and up 3, I know where the new one's going to start, and I have a good general idea for what g of x is going to look like.